Thank you. So this is joint work with Maietti. So who's afraid of extensionality? And in this work, extensionality, I see a lot of hand raising. In this work, extensionality means full extensionality, full equality reflection. So, well, we know that it is easy to work in an extensional type theory. The mathematical practice is very easy to perform on pen and paper. And we know that you don't have to enter in hell, setoid hell, or transport hell, staying extensional. And moreover, extensional type theories enjoy quite nice, beautiful categorical semantics. But we all know that in an extensional type theory, judgments are not decidable. So we cannot hope for a normalization procedure for their terms. And therefore, we also know that they are pretty difficult to implement in proof assistance, but not impossible. So one way out of this situation, a very popular way to tackle this problem, is just to design intentional theories with extensional features. For example, univalence, which is a kind of extensionality for universes, or for example, vanilla Agda implements the uniqueness of identity proof, but don't take both because there will be problems. But in this work, we follow a radically different approach, namely that of two-level foundations. Mind you, not to be confused with two-level type theories, which are for a totally different purpose. Well, not totally different because they still relate to the extensional versus intentional debate, but they are more on the first paradigm, that of designing intentional theories with extensional features. While two-level foundations say just embrace extensionality. And the recipe is the following. You start with an intentional type theory. So the computational content is on the surface into your decidable judgments. Everything is under control. Fine. And this is the intended theory for computer scientists. That's great. Then you start forgetting irrelevant computational information, irrelevant for the mathematician. For example, you don't want to keep track of explicit proof terms. You want proof irrelevance. You want to relax some equality, of course. So you get, in the end, an extensional type theory, full extensional again. Now, of course, the judgments are no longer decidable, and their computational content is hidden in their derivations. Okay, so what's the missing ingredient here? To have a two-level foundation, you should also design an interpretation which reads off the derivation of an extensional judgment and extracts its computational content in the form of an intentional derivable, decidable judgment. Okay, this has been done for the minimalist foundation, the main example of a two-level foundation. So the selling point of the minimalist foundation is it formalizes agnostic mathematics. So if you prove a theorem in the minimalist foundation, there are interpretations that allows you to write the same proof in any other foundation. For example, homotopy theory, the internal language of a topos, also constructive axiomatic set theory, the calculus of construction. And of course, it is a two-level foundation, so it starts with an intentional level, which in this case is a roughly intentional Martin-Löf type theory plus a primitively defined notion of propositions. It has an extensional level, which is, again, a version of extensional Martin-Löf plus primitive propositions plus quotients, because recall that extensional levels are intended for mathematicians. So mathematicians want quotients. And there is a restore interpretation using a setoid model. So as a mathematician, you can work in the extensional level, and you do not have to worry about encoding stuff with setoids. You are in heaven now. The restore interpretation has done that once and for all. So you can always translate everything you do in an intentional theory, but it is mechanized. Okay, but don't worry, this is not a topic, talk about the minimalist foundation. This is a talk about the calculus of construction. Our goal is to design a two-level foundation which has as the intentional level the calculus of constructions. And the main observation, the leading idea, is the fact that the minimalist foundation can be considered a predicative version of the calculus of construction. So we tried to lift all the results of the minimalist foundation to an impredicative setting. Okay, so let's start. We said that we want to take the calculus of construction as our intentional level. Actually, we took something more. We considered the calculus of construction plus cumulativity. So every proposition is also a type. And some very basic inductive types, the ones from vanilla Martin-Löf. Then, as the extension level, we took the impredicative version of the extensional level of the minimalist foundation, namely extensional Martin-Löf tape theory, primitively defined propositions, quotient types, and power types. A canonical element of a power type is just a subset obtained by comprehension by a predicate, and well, it behaves as you would expect. Okay, and in this setting, you can show that you can lift the restore interpretation of the minimalist foundation to these two theories. Okay, great. Then we proceeded to investigate this foundation, both from a proof theoretical perspective and a semantical perspective. Okay, let's start with the proof theory. So, by the way, yes, I was forgetting. As a big future work, there is implementing all this stuff, formalizing all this stuff, and possibly extending this foundation to the calculus of inductive construction. So adding a tower of universes and a general scheme of induction. But I think it's pretty difficult to. Okay, so we managed to derive some equiconsistency results, starting with the fact that the two levels of this foundation are equiconsistent. So they have the same proof theoretic strength. Okay, that's nice to know. We can also be more precise than that. We can show that actually they prove the same arithmetical statements. So if you have statements regarding just natural numbers or a subset of subsets of natural numbers and so on, then it doesn't matter if you're working in the extensional level or in the intentional one. That's a nice thing to know. And finally, we can define a classical version of this foundation by just taking the extensional level and postulating the excluded middle. And we showed that it is still equiconsistent with the default intuitionistic version via a very simple double negation translation. Okay, that's it for proof theory. What about categorical semantics? Well, it turns out that it can be expressed very nicely using quasi-toposes. Quasi-toposes are a generalization of the notion of elementary toposes, in which instead of a subobject classifier, so something that classifies equivalence classes of monomorphisms, you just have a regular subobject classifier. What is a regular monomorphism? It's just a monomorphism that is the equalizer of some pair of parallel arrows. And you need to postulate the finite colimits, whereas in the definition of a topos, you can derive them. Okay, and of course we say that a quasi-topos is arithmetical if it has, moreover, a natural number object. And with this, we can prove that there is an equivalence of categories. From the semantical side, we have the category of arithmetical quasi-toposes. On the other side, the syntactical side, we have syntactical theories built over the bare calculus, the extensional calculus. And of course, the two factors are the usual one, the construction of the syntactic category and the extraction of the internal language of a category. There is an asterisk near theorem because this can be shown to be either a B equivalence if you relax the morphisms of the syntactical morphisms, or a kind of a relative coadjunction which is familiar from the work by Maietti. And that's all. Thank you for your attention.